switch off the video for that we will have a better connection. Right. Now, I hope all of you can see my shared PowerPoint slides. And please let me know if there is any difficulty of viewing the slides or anything like that. Right. Now, for some reason, my regular way of doing the lecture, which is the live version of the presentation that you can see from your screen, is not working for these 2 weeks for some reason. So I will just use the powerful PowerPoint slides because of that. Right. Now, when we think about the life cycle of the stars, even though you feel that the stars that you see above your head or up in the sky seems to be there forever, it is not the case, right? Stars do not live forever. So they radiate light, and what happens is, as a result of that, they will slowly deplete their energy reserves, right? So the star is kind of an energy storing device. So there are a huge amount of energy inside the star, and you will learn why I am telling it in coming lectures. So what will happen is it will radiate light by consuming this energy, and then one day, so this will actually change the properties of a star, such as the color, temperature, brightness, those kind of things, right? Now, when we look at the sky, there is an evidence for that as well, because when you don't see all the stars in the same color or in the same brightness, right? So the different stars has different properties, like different brightness and different colors, like that. The properties are different. Now, the main reason for this difference is that they are actually different stages of their life cycle, right? Each and every star has its own life cycle, like for us. So we have our own life cycle, like that. Each and every star has different life cycle. And the reason that you see the stars in different brightness and different colors, so that means in different properties, is that they are actually spending their life at different stages, right? So that is the reason. And right. Now, when you talk about the first stage of the life cycle of a star, is its initial birth, or the formation of the star out of interstellar matter, right? Interstellar matter is what we are going to talk about today. So interstellar matter is the matter that we have in between stars, right? Now, in fact, the first step of a life cycle of a star is the birth of the star, and that birth happens out of this interstellar matter, or using the interstellar matter available in between stars, right? And then once in this period, actually, the most of the stars, they experience a very lengthy period of stability after that, right? And at the end, all the stars will run out of its fuel, which means their energy, and then will die at some point. So that's basically what will happen to a star. Now, when we talk about the basic ingredients of the stars, as I told you, stars made out of raw materials available in the space. So that space is the space in between stars. And this material, we have a specific name, and we call this material in between stars, or raw materials for the stars, as interstellar matter, right? So make sure that you remember that name. And interstellar matter is generally found, as I told you, in between stars. And this material is not spread evenly throughout the universe, like stars is usually found in galaxies. So that what that means is this interstellar matter is not spread like evenly throughout the whole universe, right? Mostly interstellar matter is found inside galaxies, right? So that's why you have a lot of stars in galaxies. And composition of this material is similar to composition of the stars and large planets. Now that gives you an idea that probably the stars are made out of this interstellar matter. The reason is, if you look at the composition of a star and composition of interstellar matter, they are basically similar, right? The composition doesn't change, right? Now, this is one of the reasons that we believe interstellar matter provides raw material to use and make these stars, right? So that you have to understand, right? So that's obvious now. If the composition is similar in stars and interstellar matter, then we can think that probably interstellar matter is the material that helps to create stars, right? Now here is, so let's go and look at different types of interstellar matter, right? Because if interstellar matter is responsible for creating stars, then we need to, study a little bit more about interstellar matter in order to better understand about the birth of a star, right? So there are different types of interstellar matter. Now this image that you see in the left-hand side basically explain those different types of interstellar matter. Now this, so there is a red color nebula right here, the reddish nebula. That means this region right here is that reddish nebula. So this is actually a photograph that glow with light emitted by hydrogen atoms, right? So normally when a hydrogen atom emits light, so that mostly comes in the alpha region, which is basically the red wavelength, inside the red wavelength. So that's why you have this reddish color when you have hydrogen atoms, right? And then there is a dark area, right? Like this area, right? So that area is relatively darker. And that particular area is, that's because of, it is actually dark. That's because that particular area has blocked out all the stars behind that. So there should be some stars that are emitting light, but this particular area is dark because the interstellar matter basically consists of mostly dust inside in this area. So because of that, this dust particle absorb all the light behind this the stars. Sorry, dust particles absorb all the light coming from the stars behind it, and because of that, you see a dark cloud in that region, right? And then there is another region in the top right-hand corner, this blue region right here, right? So that is again another type of interstellar matter. And what has happened here is actually, so there are some hot stars around this region, and these hot stars actually emit light, or the light emitting from those stars get reflected from the cloud, dust and gas inside in this area. So that particular area has become bluer, right? And apart from that, there are some other information. This particular star right here is a supergiant star. So you will understand what supergiant star means. And the star is actually Antares. So this can be easily seen in a clear night if you are in the correct time of the year up in the sky. So you can see that interstellar matter has different properties, right? So in this side, it's kind of dark, and this is bluish, and that depends on what kind of processes that you have in that particular region, right? Combining both stars and interstellar matter, right? So if you look at the composition of interstellar matter, 90% of the particles in interstellar matter are hydrogen atoms or molecules, right? So the 90% is hydrogen, and out of rest of the 10%, around 9% of the particles are in the form of helium atoms, right? Right now you can understand that 99% of the interstellar matter is hydrogen and helium. In fact, almost 90% is hydrogen, and then you have helium, right? And all the other elements make up remaining 1%, right? astronomers often refer to these elements as metals. So that 1% normally consists of like oxygen, carbon, nitrogen, iron, those kind of elements, right? So that's the basic like composition of interstellar material. You can see 90% hydrogen, 9% just helium, and all the other metals and elements consist within that rest of the 1%, right? And if you divide this interstellar matter in a particular way, specifically in another way, there are basically two components. So that is gas and dust, basically hydrogen, helium. So those are kind of gas, right? And apart from that, there is dust particles in interstellar matter as well. And because of that, we used to tell that the two main components of the interstellar matter is gas and dust. This individual interstellar gas consists of mostly individual atoms, and I have given you the typical size. It's in around the 0.1 nanometer range. And as you saw in the previous slide, hydrogen atoms are the most common one. And then the molecules that you have in interstellar gas is like water and oxygen, right? So those kind of molecules. And they are about typically 1 nanometer in size, as you can see here. And on the other hand, the dust consists of clumps of atoms and molecules. Again, you have the atoms and molecule as dust. And these dust mainly made of elements such as silicon, graphite, iron, those kind of things, right? These solid dust particles are typically around 100 nanometers in size, and they are similar to those that make up of smoke, fog, haze here on Earth. So these dust particles are kind of similar to the fog or the haze that we see on the Earth, right? Sometimes in the morning, you see the fog, right? So when you have the fog, it is hard to, the visibility goes low, right? So hard to see something that is so far away, right? So this exact thing happened because of the dust as well. If you have a lot of dust particles, then you cannot, it's hard for you to see the things beyond those dust, right? So that's why you had those dark regions in the interstellar matter that I have shown you in the previous image. And in terms of the temperature, the interstellar matter normally we consider as a very cool, cool regions. Typical temperature is around 100 Kelvin. But when you think about the interstellar matter close to stars, right? So when you have a large number of stars, the interstellar matter, because of the energy releasing from the stars, this interstellar matter get heated up. Because of that, the close to stars interstellar matter can be as hot as around 10,000 Kelvin, right? And if you think about the interstellar gas, the gas used to be very sparse, so that means the number density is very low. So that is about 10 to the power 6 particles per cubic meters, right? So the numbers, you mean this is again a high number, but if you compare it with the air, it's around 10 to the power 25 particles per cubic meter, right? So you can see how less dense is the numbers, how low the number density for interstellar gas compared to our normal air, right? And if you think about the dust, it's extremely sparse. So that means it's even more lower in terms of the number density. And the number is 10 to the power minus 6 particles per cubic meter. So that's a very small amount, right? So that's why we used to tell that the interstellar gas is very sparse and dust is extremely sparse because it's a very low number density, right? Right. Now, even though this number density is very low in interstellar material, the total mass is substantial as the volume of space in which such matter is found is huge. So that's because even the number density is very low, the amount of volume that you have in space is huge, right? And because of that, the total mass for interstellar matter is substantial. So that's a large amount, even though the number density is low. And the reason is because of the amount of space that it takes is very huge, large, right? Now, something that you may be surprised if you have not heard before, the stars actually only take a tiny fraction of volume of the Milky Way galaxy, right? So we have this conception that everything that we see in the Milky Way should be stars, but that is not true. Milky Way is the stars is actually a tiny fraction of the volume that of the Milky Way, right? So mostly what we have is interstellar matter, right? Right. Uh, Now, one good example for that is how rare the stars are. Uh, Light only take about 4 seconds to travel a distance equal to the diameter of the sun, right? But take more than 4 years to travel from the sun to the nearest star. So that basically tells you how far away our next star is, right? So in between that, you don't have any other stars, right? So that's why we used to tell that the stars are actually a tiny fraction, right? I mean, for the nearest star, we have to go for more than 4 years, right? Right. Now, you can actually estimate the mass of the interstellar mass in our galaxy. So that is just in the usual way how you use calculate the mass. So that is the volume multiplied by density of atom multiplied by mass per atom. And I have given you the numbers here. Suppose that the average density of hydrogen gas in our galaxy is 1 atom per cubic centimeter, and each hydrogen atom has mass of 1.7 times 10 to the power minus 27 kilogram. And if the galaxy is a cylinder with a diameter of 100,000 light years and a height of 300 light years, what is the mass of this gas and how many solar mass stars could be produced from this mass of gas if it were all turned into stars, right? So this is a nice example for you to work yourself. And as you can, you will understand that there is nothing special. You just plug the values to this particular equation to find the total mass, right? So there is nothing special about it. So try it yourself and try to find an answer for that, right? Right. So we'll move on to the next section. Probably in the next lecture, we will try to, so try this yourself. So we will try to discuss in, at some point in our lectures to find the answer, right? So these kind of simple calculations, I expect you can do that, right? I mean, except that you need to understand the basics of astronomy. Other than that, the calculation is straightforward, right? You know how to find the mass. And only thing that you need to assume here is uh, when you try to find the volume for the galaxy, assume that we have a cylindrical shape for the galaxy, right? When you assume when you try to find the volume, right? So that may be easier. So it has mentioned here as well, if the galaxy is a cylinder with diameter of 100,000 light years and the height of 300 light years, right? So you have all the information, height and the diameter, so which means you can find the volume and then plug the density of atoms and the mass per atom here to find the total mass, right? So that's how you estimate the total mass of a galaxy. Right, now let's look at, by the way, let me explain a little bit about these two pictures. This is once again the Orion Nebula. The two images that I just showed you here is just for a practical reason. The one that you see in the left-hand side is the image of the Orion Nebula. It's a colored image, and these images are the images that you more frequently see in the internet if you browse and try to find the image of Orion Nebula. However, this is not a direct image taken from a telescope, right? So what they have done is you take the same image using number of filters and then you combine it, right? All the filters to make these colors, right? So that's how you make these pretty pictures in astronomy. However, on the one on the right hand side, I just need to show you how these things work practically. What you see in the right hand side is an actual image directly taken from the telescope, right? So it's the same Orion Nebula, and actually I have taken this image in the left hand side using the 0.9-meter telescope at the Kitt Peak National Observatory, Tucson, Arizona. I guess this is around 6 years ago now, around 2016 or 17. And that is what you normally see from a, if you are in a telescope at the first time, right? So you can see it's coming as a black and white image in a using a CCD camera. And this is using a particular one filter. I think this may be the red filter. I can't remember which filter that I have used. And then you change the filter and take the same image again, and then change the filter and take the same image again, right? Like that, you do it few times from different filters, and then you combine it to make these colors, right? So that's how you get the colors for this image. So that's a different story. What I want you to teach here is when you have, all of you know that the Orion Nebula is it's a nebula, so that means this is a site for young hot star formations. There are a lot of young stars forming in this region, right? And so what actually happened is when there are a large number of young stars forming in a certain region, these hot stars, if the stars are new, they will be hot stars, so their temperature will be larger, so they will actually heat the nearby gas, right? Heat the surrounding interstellar gas, and this heat can go up to around 10,000 Kelvin. And at the same time, there are ultraviolet radiation that coming from those stars, and this ultraviolet radiation can also ionize the hydrogen. So this hydrogen that I am talking is the hydrogen in the interstellar matter. So once again, if you have hot stars in a certain region, those hot stars can heat the nearby gas. So the nearby gas is in the interstellar matter, and apart from this, these hot stars also emit ultraviolet radiation, which can this ultraviolet radiation can ionize the hydrogen, right? So then you will have ionized hydrogen as well. Now, if you take a typical moment, most of the atoms near the hot star are in the ionized state. So that's because that you have a hot star. So because of that, when you have hot stars, they are these hydrogen atoms are in the ionized state, right? And this is actually when you need to detect new star forming regions, we use this method, right? Because we know that if you have new stars forming, they emit a lot of ultraviolet radiation, which will ionize the hydrogen, right? So when hydrogen is ionized, what happens is they will go into higher energy states and then will come down to lower energy state. Now, when this happens, when the energy comes into lower states, they emit H alpha emission. There will be a total H alpha flux coming out of those regions, right? And then if you have a good filter like H alpha filter, then you can use that filter to detect all these H alpha flux coming from this region, right? So on the other hand, if you can detect a lot of H alpha in a certain region, you can straight away tell that there are large number of hot young stars in that region, right? So I hope this will it will make it clear for you. And right. Now you can see that around these ionized, when you have these hot star forming regions, around those regions, you will have ionized hydrogen, right? If not, actually, when you go for a little bit far away from these hot star forming regions, you will mostly have neutral hydrogen without ionization. Now, it is important that this convention that we use in astronomy, which is maybe different, little bit different than what you use in chemistry. So we often characterize the region of the space according to whether its hydrogen is neutralized or ionized, right? So we normally, when you look at a certain region in the space, we basically need to tell whether the hydrogen is ionized or whether you have neutralized hydrogen in that region, right? And ionized hydrogen we normally call it as H2 region, right? Now the reason is, I have given you inside the bracket, Roman numeral 1 is used to indicate that an atom is neutral, right? So if you have just 1, then that means that particular atom is neutral. If you have 2, that refers that it has lost 1 electron, right? For example, I have given you Fe3, so that means Fe3 means it has lost 2 electrons, right? So always there should be 1 lower than the number that you have in the Roman letters. Right. Now with these H2 regions, if you have H2 regions, then you will have this red hydrogen line in the spectrum, right? Right, so that's about the ionized, how to detect ionized hydrogen. You can see that if the hydrogen is ionized, then you can detect it from a spectroscope or something like that, right? From the spectrum of in that particular region. Right, now when you look at the neutral hydrogen clouds, so the neutral hydrogen is the one that is mostly available as the interstellar matter, because you get ionized hydrogen only around the regions where you have hot stars forming, right? Because of that, as it is obvious, most of the volume of the interstellar matter is filled with neutral hydrogen, and the problem with the neutral hydrogen is that it neither emit nor absorb light in the visible part of the spectrum, right? So there is no evidence in the visible part to detect this neutral hydrogen. They even don't absorb or emit any kind of visible light. So that means from optical telescopes, we will never be able to detect this neutral hydrogen in interstellar atmosphere or interstellar matter, right? But there are some other elements that can absorb visible light, even even at typical interstellar temperatures. So there is one example right here. So you have a star right here, and then if you have an interstellar dust or cloud, it is trying to get a spectrum by an observer, you will get broad absorption line for the materials in stars, and then there will be another set of absorption lines, but their lines are a little bit narrower. So those narrow lines come because of the presence of this interstellar dust cloud, right? These narrow lines will show you what kind of elements that you have in interstellar matter in that case, right? And as I have mentioned here, the sum of the strongest interstellar absorption lines are produced by calcium and sodium, right? But many other elements can be detected as well in sufficiently sensitive observations. You can see that the calcium and sodium is widely available in interstellar. You can see those in interstellar absorption lines. Now the problem is still, there is no way of detecting this neutral hydrogen, because the neutral hydrogen don't get ionized. If they don't get ionized, then there is no way of detecting those, right? So that is the problem. Now, there is one way of detecting those neutral hydrogen. So that is using this 21 centimeter line. And remember, this is very famous in astronomy for detecting hydrogen, because interstellar matter is the mostly vast available material in the galaxy, and also in that most of the interstellar matter is in the form of neutral hydrogen, and if we cannot detect neutral hydrogen, so that means we cannot detect the most important part, right? And because of that, we use this 21 centimeter line to detect neutral hydrogen. And what actually happens is you have in a hydrogen atom, you have a electron in the hydrogen atom, and that orbit around the nucleus, right? And also you have a proton at the nucleus, right, at the center. And you can see from this diagram, actually, there are two scenarios. Proton and the electron may be spinning either in the same direction or in the opposite direction, right? So you can see in this scenario, it's kind of moving in the same direction, but here the two are in the opposite direction, right? So both these things can happen. When the electron flips over, the atom gains or loses tiny bit of energy by either absorbing or emitting electromagnetic energy with the wavelength of 21 centimeters, right? So what happens is when this atom flips over, so that means you can see from the diagram A, the atom, you can see the electron is in the upward direction, and for the diagram B, it goes to the downward direction. It is this flip. What happens is when you have this flip over, the atom gains or loses a small amount of energy, right? So that's by absorbing or emitting electromagnetic energy, and that amount of electromagnetic energy corresponds to this 21 centimeter wavelength, right? And when you look at this scenario, you can see that the amount of energy that released from one such atom is a very tiny amount, even that we cannot even think about detecting that. But good thing is in interstellar matter, the amount of hydrogen is there is a large amount of hydrogen, right? And because of that, this the energies that release energy will add up, and you will have a strong line at the wavelength of 21 centimeter that you can detect, right? And here are some images and details about, first, discovery of first observations using 21 centimeter line. And this is the entire view of the sky using 21 centimeter line, right? And actually there are some other type of interstellar gas, and this is a different one, ultra hot interstellar gas. So that means the interstellar gas has a temperatures of million degrees, which is a little bit unusual compared to what we have talked before, right? So we have talked about around 10,000 Kelvin degrees of temperature for the interstellar matter when they are close to nearby these hot star forming regions. But this is a different case. There are in some instances, you have interstellar gas at a temperature of millions of degrees. So it's even a very high value. And when astronomers try to find the reason for this kind of high temperature interstellar gas, so of course you cannot do it from Earth. So what they have seen is when they look at the spectra of the atmosphere, they have seen the lines produced by oxygen atoms that have been ionized 5 times, right? So they have seen the lines produced from oxygen atom, which is ionized like 5 times. In order for an oxygen atom to ionize 5 times, you need to have an unusually enormous amount of energy, right? And then what they did was they did some subsequent observations with X-ray telescopes. And what they have revealed is that galaxies filled with numerous bubbles of X-ray emitting gas. Right? So there are bubbles of X-ray emitting gas as well inside the galaxy. Right? Now this, in order to emit X-rays and to contain oxygen atoms that have been ionized 5 times, the gas must be heated to temperatures of million degrees or more. So that's the connection between this huge temperature and the amount of atoms available, right? It's basically ionized oxygen, right? Now, in order to have this kind of remarkable temperatures, there should be a special phenomena then that happens, right? Apart from what we have discussed. Now, astronomers now believe that the reason for having these kind of very high temperature values is actually supernova explosions, right? Supernova is something, an explosion of a star, and we will discuss about that in coming chapters. There are two types of supernovas, basically type 2 and type 1. And we will have a separate section about the supernovas and their explosions. And because of that, I will not talk about supernova explosions at this point, right? So this is an example of a supernova remnant. So just go and look at those things. I'm not going to, read through each and every section, because this section is also, there are a lot of information that you have to read and understand, right? Right. So anybody have any questions up to here before I start the next part about the molecular clouds and those kind of stuff? So I will give you 1 or 2 minutes for you to just think about what we have been talking, right? Now. Right. So no questions. Right. So let me go into the next section then. So we talk about different types of interstellar gas, and then the most importantly, how we detect them in astronomy, right? And there is another uh, type which called as ultra hot interstellar gas, which are extremely hot than the usual conditions, and we believe that these extremely hot gas, which lead to ionized oxygen as well, is due to the fact that we may have supernova explosions on those regions, right? Right. So and then astronomers have also observed more complex molecules in the interstellar cloud using different spectra in radio and IR wavelengths, right? So this discovery of complex molecules in the space came as a surprise, because most of the interstellar space is filled with ultraviolet light from stars, and this light is capable of disassociating molecules. So what I am mentioning here is, when you have this in the interstellar space, you have a lot of ultraviolet light, right? And ultraviolet light is capable of disassociating molecules, and because of that, we don't expect these complex molecules to be stable in this environment. However, uh, there are significant amount of the space also contains a large amount of dust, right? So once you have this dust, the dust is capable of blocking out starlight, right? And when you have starlights blocked out by these dust particles, there will be dark clouds in those regions. So those kind of regions are the ones that you have seen in my previous picture, right? So if I go back, I'm basically talking about this picture right here. You can see these dark regions right here. So those are the regions basically that the light is blocked by the dust inside this region, right? So that's what I am talking here. That's this one right here. And this is where you have these dark clouds, right? And these clouds can block ultraviolet starlight, and hence molecules can survive, right? So gravity also helps the interstellar gas together to form a giant molecular cloud. Now, what this explains is we have some observations to see that there are more complex molecules available in the space. However, due to the presence of the ultraviolet light from stars, because stars emit ultraviolet light, normally ultraviolet light is capable of disassociating these molecules, right? So because of that, we normally don't expect to have more complex molecules in interstellar matter. However, there are certain regions in the sky that has a lot of dust which blocks the starlight coming past those regions, and because of that, those regions be visible as darker regions, and around this region there is a possibility to form giant molecular clouds, right? Because there are no ultraviolet available in those regions, right? So that's what I am trying to explain here. And here is an example, such example for a area that you have a lot of dust. And this particular area right here, you can see that it's completely black, that you cannot see anything, right? And you should understand when you look at the background, there should be something special about this particular region for not to visible these stars, right? Obviously, that's because there are no stars. The reason is actually there is a lot of dust inside this region. So the dust has blocked all the starlight, right? So that you just see this dark region. And here is one example for one of these more complex molecules in the interstellar matter. And of course, there should be a way to detect dust as well, right? If the dust block all the other type of energy, right? So by blocking the light from the distant stars, they are actually emitting energy in the IR part of the spectrum, right? So this, if you can detect that, then you can detect the dust as well. Right? So I'm just going to a little bit quickly in these few of these slides, because these are actually widely you can read and understand most of the things, right? And this is also a region that dust particles are actually blow up by the light from stars. And there are certain things that I am now going to assign you for read yourself in this presentation, that is about the reflection nebula. One. And then this interstellar reddening, all the material is available here, right? So I would like to read you an understanding, but let me brief what I am trying to mention here, right? I have basically defined what a reflection nebula is in this particular section. And here there is a concept called interstellar reddening. So what that means is, I have explained here that when you have interstellar dust grains, they absorb some of the starlight, and then at least half of the starlights that interact with the dust also scatters, right? So from the dust, what happens is all the starlight is either absorbed or scattered, right? So once the light is absorbed or scattered, the stars will look dimmer for us, but actually they should not that much dim, so that the decrease of the brightness comes due to the fact that the absorption and the scattering of this light coming from stars by this dust particle, right? Now this effect is what we called as the interstellar extinction, right? Because of this extinction, you get less light from the stars than what you expect, right? And the other thing is because of this effect, it is not only the stars is dimmed, but also all the light that you get is also reddened by the interstellar dust. So that means they have moved into the red region, right? So this particular phenomena has a special name also. We call it as the interstellar reddening. And this is the image is the same image that you have seen here, right here, in a different orientation, but you can now see that inside this dark region you have the top red dots that represent the stars and probably maybe other objects, right? And that came because you have taken the image using a different wavelength band, right? Basically, this is actually IR image. So this is the embedded IR image, so that you can see a lot of objects can be seen using IR, but not visible light in that particular region. So this also explain what is extinction means. I think you can read and understand that part as well. Right now, up to here, what we have discussed is about interstellar matter and the composition of the interstellar matter and how we detect those kind of things, right? Now, we have to connect this story for the formation of the stars. Now we know what is interstellar matter, what kind of material available inside the interstellar matter, and how can we detect interstellar matter, and how can we understand interstellar matter, those kind of things. Now we need to make a connection how the stars are forming from interstellar matter, like what are the conditions that we have to satisfy with that, right? Because the interstellar matter is available in everywhere, but we don't see stars in everywhere. So there should be a reason, or there should be a set of things that should be satisfied by the interstellar matter in order to create a star or stars, right? So we are going to look at that particular part now. So to start with, if we think about what is the fundamental difference between the interstellar matter and the star, they are both composed with similar mixture of elements, that is hydrogen and helium basically. However, the difference with the star and the interstellar matter is the star is so dense that the pressure in its center creates temperatures hot enough to burn hydrogen. So that is the specialty about the star, right? The star is very dense, and because of that, it should have a high pressure at the center of that particular star. This temperature is enough to burn hydrogen, right? So that's why basically why most stars are actually shining. Right now, this actually finishes my section about the interstellar matter. Anybody have any questions?